All right, let's look at Euler's method in this one, and that is pronounced Euler, not Euler. And what Euler's method is it's a way to approximate function values when you are given a differential equation and an initial condition. If it is possible to find the solution to the differential equation, then usually we'll go that way, because if you can find the solution, then you can get exact function values without having to do approximations. However, some differential equations are extremely difficult to solve or impossible to solve as far as we're concerned. And in those cases, it is easier, or the best way is just to do Euler's method and get an approximation. Now that's all kind of speaking in vague terms because you have no clue what Euler's method is. So what I'll do is I'm going to give you 3 examples of Euler's method and how it works. And we have actually kind of done a little Euler's method in the past. And what we're going to do for this one and this one only, we're actually going to look at the graph and kind of think in terms of slope fields and stuff. But what I've done is I've given you a differential equation, dy dx is x plus y. I've given you an initial condition, so I'm starting at the point negative 1, 1. There's where my function begins. And what I want you to do is use a delta x of 1, that is also sometimes referred to as the step size. Some books call it h. Some books will say h equals 1. I'm not sure where they got h, but whatever. A step size of 1 to estimate f of 1. Now, if we're going by changes of 1, and we're going to go from negative 1 to 1, we're going to have to do 2 steps. We'll go from negative 1 to 0, and then we'll go from 0 to 1, and that will give us our approximation at 1. And all we know about the function is that its slope is given by x plus y. So we're going to start with this point right here, which is the ordered pair negative 1, 1. And if I plug that into the differential equation, so we'll have some ordered pairs. So if I have x, y, the differential equation, dy dx is x plus y. I have no idea why I wrote that equal sign right there. And I am starting at the ordered pair negative 1, 1. If you add those two together, you get a slope of 0. So what I know about my function is that at this point we have a slope of 0. So what we'll do, as inaccurate as it is, we will assume we carry that slope, and we're using a change of x of 1. So I'm going to carry that slope all the way over for a length of 1, since that was my change in x, and I am now at the ordered pair 0, 0. Holy cow, this is a terrible problem. Wait, that's a 0, 1. I don't know my ordered pairs. Whatever. All right, so we are now at the ordered pair 0, 1. Well, I'm going to recalculate my slope because I've gone my first step. I'm going to recalculate my slope. 0 plus 1 is 1. And so I will adjust my graph, and my graph will now change to a slope of 1, and I will carry out my slope of 1 until I get to my next x coordinate. That was terrible. I suck at connecting dots. There we go. So I carry out a slope of 1 for another length of 1, because that was my change in x, and I'm now at the point 1, 2. Well, I'm now at 1, so what we'll say is that f of 1, by Euler's method, by carrying out these slopes for the predetermined length of x, we carried out those slopes, and we got f of 1 to be approximately 2. Now that's not very accurate. If you wanted it to be more accurate, then you would use smaller step sizes. You can go like by 0.5s or by 0.1s. If you take a sufficiently small enough change in x, then you can get a very accurate approximation. But that is the meat of what Euler's method is. We just take the slope that's given and we extrapolate that over whatever the delta x is until we get to the predetermined x coordinate. And in this case it was 2. Now for the next 2 examples, we're going to look at it in a different way. We're going to do it without graphing. So I've given you another differential equation. I've given you the step size. Now we're going up by 0.5s. We're not going up by whole x's. And I want to go from x equals 0 all the way to x equals 2. Now I said y of 0 and y of 2 instead of f of 0 and f of 2, but it's the same thing. And the way I organize these is through a table. So in my table, I'll have my x coordinates, I'll have my y coordinates, and then what I'm going to do is I'm going to take my differential equation, which is dy dx, and I'm going to multiply both sides by dx. So dy is 2x plus y dx. And the reason I am doing that, that's going to go in this last part of my table. So let me fill out my table here. There we go. And this dy dx thing is going to go right here. The dy equals 2x plus y. Sorry, plus y. Dx. And what we know is that we're starting at the point 0, 1. That's my initial point. We also know my step sizes are by 0.5. So I could actually go ahead and fill out my x's. I know that I'm starting at 0. If I go up by 0.5s, my next one's going to be at 0.5. My next one's going to be at 1.0. My next one's going to be at 1.5. My next one's going to be at 2. And I'll actually stop there because we're trying to approximate f of 2. So I'm going to go ahead and draw out my table a little bit more here. What we do not know is what the y coordinates are. I know what my change in x is. What I don't know is how much my y changes, and that's really the challenge in these problems, is to find out how much your y changes. If we look at this thing, we knew that I was going to go up to 0 and then up to 1 on my x's. What we had to figure out is how much my y changed. We initially did not change the y's, but then my y changed by 1. We went from 1 up to 2. This is why I solved the differential equation for dy, because if you remember, the dy does represent a change in y. That's what the d stands for. It actually is a change in y is equal to 2x plus y times the change in x. The d does kind of replace the delta, so I'm going to alter this to reflect that. It's delta y equals 2x plus y delta x, right? But we know that delta x is 0.5, so I could actually carry that one step further and say that it's 2x plus y times my delta x, which is 0.5. And what I'm going to do is we know our x coordinates, we know the change in x. I'm simply going to plug that into my equation for delta y. Delta y is 2x plus y times 0.5, so my first one is going to be 2 times x, which is 2 times 0, plus my y coordinate, which is 1, times 0.5. That's 0 plus 1 times 0.5. That is 0.5. And what that does is it tells me how much my y changes. That is my change in y. So if I started at a y coordinate of 1 and my change in y is 0.5, then I'm going to add 0.5 to get to my next y coordinate. So I'm now at 1.5. This table is designed to tell me how much the y is changing. Now once I have my new y coordinate, well, now I plug into my differential equation, 2x plus y times 0.5, so that's 2 times my x, which is 0.5, plus y, which is 1.5, times my delta x, which is 0.5. And you will be using your calculators on these most of the time. If it's a non-calculator question, then the numbers end up being very nice. This is 1.25. Now that's my change in y, which means I now need to add 1.25 right here, which gives you a new y coordinate of 2.75. And then we simply repeat that process. So now it's 2 times my x coordinate, 2 times 1, plus my y coordinate, 2.75, times my delta x, which is 0.5. We'll throw that in the calculator, and that's going to give you 2.375. I've already worked these out, so saving a little bit of time. So now I have my change in y. I'm going to go back and add that, plus 2.375. And when you add that, you will get 5.125. 5.125. Plug in again. 2 times my x coordinate plus 5.125 times my change in x, which is 0.5. And I'm simply plugging into this formula up here. And when you do that, you will get 4.0625. And then finally, our answer is going to be whatever this is plus 4.0625. And when you add those together, you get a final y coordinate of 9.1875. And that is what we are estimating y of 2 to be. So we'll say that my function's value at an x coordinate of 2 is approximately, it's not exact, but this is approximately 9.1875. That was a fairly ugly one. Usually they don't get that bad. On the AP exam, they do keep it fairly simple. Usually it's only like 2 steps or 3 steps. They just want you to show that you know what to do. But the challenge is to find your change in y, and then you add that change in y to the previous y coordinate. So there we go. Let's do one more. There's my differential equation, dy dx equals that. We're using Euler's method with 3 steps. Now this one, notice I didn't tell you what the change in x was. We're starting at 0. We're going to 1.5. So you're going to have to figure out what your change in x is going to be. Well, 0 to 1.5 in 3 steps would be a change in x of 0.5, just like that last problem. So I'll set up the table. Alright, so there's our table. I went ahead and multiplied both sides of this differential equation by dx so I could get my delta y equals x squared plus y delta x. But remember, delta x is 0.5, so we'll kind of make a little note that that's equal to 0.5. And then we start plugging in. So x squared, 0 squared, plus y, which is 1, times my delta x, which is 0.5. That equals 0.5. So I need to add that change in y. That's how much y changes. I'm going to add that to my previous y coordinate, which gives me my new y coordinate of 1.5. And now one thing I forgot to do, I need to go ahead and pull my x's down. I know we're going up by 0.5s, so 0 to 0.5 plus 0.5 is 1 plus 0.5 is 1.5. So my change in x is going to be 0.5 takes me to 1.5 in 3 steps. So now I know my new x and y, so it's going to be x squared, so 0.5 squared plus 1.5 times my change in x, which is also 0.5. And when you throw that in the calculator, you will get 0.875. So now I add that plus 0.875. And when you add that, you will get a new y coordinate of 1.6875. And then one last time, x squared plus 1.6875. And remember, do not round your y coordinates or your y values in the intermediate steps. You only round at the very end. When you plug all that in, you will get, hang on, I messed up. Alright, not a huge mistake. I was looking down at the work that I've already done. This is 1.5 plus that is not, that's 2.375. 2.375, so that's going to be 2.375 here. I just wrote down the wrong number from my work, wasn't paying attention. And this is where 1.6875 is. Okay, so my bad. Add 0.875 to your previous y right here. That gives you 2.375 as your new y coordinate, and then you plug in 1 and 2.375 to your delta y equation. You get 1.6875, so now I'll go back and add 1.6875 here, and when you add that to your previous y, you will get your final y coordinate of 4.0625. So we will say that y of 1.5 is approximately 4.0625. And that is what Euler's method gives you for the approximation at 1.5. So the challenge is simply, well, I say simple, but the challenge is to find your change in y. Once you find your change in y, then you add it and you keep working those steps. And they're kind of tedious and monotonous. You have to be kind of careful with your work, hence the table. But there you go.